It doesn't hit 0 because if you plug in 0 to the function, you just get 0 as output.
Oh, I mean, well, it's a perfect.
So there is a point at 0, 0.
Wait, but if you like zoom in, you're not gonna.
If we zoom in, what are we gonna see?
You're just gonna see it get progressively closer to 0.
Right? What
there
are
a
the features
what
of that
0?
graph that we see if we keep zooming in right here?
I'm
What
zooming
features are-
farther and farther in, and it's looking more and more vertical.
There you go, that's something. Here you go. We keep zooming in right here. What is happening? If I stop changing the scale. What's happening?
It's becoming vertical.
Yeah,
Oh,
it's becoming.
if it was at 0, it would not pass the vertical line test.
So
so
this
the
does pass the vertical line test at the point at 0, 0.
Well, it's an inflection point, right?
No, because we're going concave down to concave down. Okay, you said it's getting vertical. We can work with that. What's the derivative of a vertical line?
Nothing.
Doesn't undefined. Doesn't exist. Okay. So if we're getting gradually closer to a vertical line for our tangent line at 0, what's the slope of a vertical line?
Nothing.
Yeah, undefined.
So it just so like it would.
Okay. Or we could say, what's happening at this point? Are we becoming locally linear here? Are we looking at a straight line as we get closer and closer on both sides of 0? Or what does this kind of remind you of?
It reminds me of. I don't know.
What's another graph that kind of looks like this?
I could tell you.
Absolute value?
Oh, yeah.
Can we take the absolute? Can we take the derivative at 0 of the absolute value function?
Nope.
Why not?
The absolute value of 0 is 0. I guess it is. Oh, because then it's a linear line.
Yeah, I mean, if I'm zooming in here, the absolute value never really becomes linear. Right? It doesn't become locally linear. There's still this point here. It's still like changes fast. It's not like a smooth, continuous. Like, it's continuous because all of the points are there, but it's not smooth. It's not nice. It's not slowly changing. It has a corner or
which
cusp.
it has a cusp, and which is what makes it not a function. It makes it discontinuous.
Nope, it's still continuous.
Non-derivative,
Differential.
non-differential.
Because it has a corner or a cusp.
Yeah.
Right, because it has that point. That cusp is what we call it in math, but because of that, you can't take the derivative at that point. Because let's think about it. Let's just go back to our basic definition of the derivative. It's the rate of change at a point. Now, the rate of change as we're approaching 0 from the left. What's the rate of change as we're approaching 0 from the left? Don't worry about the scales. Just think about absolute value function.
Oh, it's negative.
Negative. What? Negative.
1.
Yeah, -1. That'll be the slope as we're coming from the left. What's the slope as we're coming from the right?
Negative 1. As we're coming from the right, we're going.
What's the rate of change as we come in towards 0 from the right? Don't look at this scale.
Negative 1.
No.
Positive.
What's the slope, Jonah, as we come in towards 0 from the right?
For the
What's the rate of change here for the absolute value function?
would be just 1/1. So it's going closer to 0, so it'd be negative. It'd be a negative slope. Well, negative slope in the sense that it's like decreasing. So
Okay.
you can't really do that.
But is the slope,
so
is the rate of change the same all along here?
Yeah.
So it doesn't change, it doesn't increase or decrease, it doesn't become negative. Here is a negative slope, here's a negative rate of change as we get closer to 0, of -1. So the slope on this side
Is
+1.
but it's not because if you're coming from the right to the middle, you're going down.
No, it's like if I hold up a pencil to it, like I'm looking at it, but what's the actual slope there? Like, I'm just saying as I travel this way, as I travel this way on the x-axis, what kind of slope am I looking at all along the way?
Positive.
A +1 slope. It doesn't look like 1 because of the scale, but it's a +1 slope. Okay. As I'm traveling this way, it's a -1 slope. Okay. All of that to say, I have a -1 slope and a +1 slope, so when I come to 0, if I take the limit of both sides, yeah, I don't have the same slope on both sides, or at least they're not tending towards the same slope. This slope, as I take the limit from the right towards 0, the slope here is +1, and it's tending towards +1. When I take the limit of the slope on this side, it's tending towards -1. So because the limits don't match up on either side of the absolute value function, because I have 1, -1 on either side, then it's just not differentiable at 0 because the limits don't match. Now, if I had this function, it's the same reasoning. I mean, what's the slope here? Some kind of positive something, some kind of negative something, but they're not both tending towards the same value. So because there's this little cusp here for the red one, right, it's not, you can't take the derivative. Does that make sense?
Yeah.
That's where differentiability continuity, that video, comes into play too. These are continuous functions, they pass the vertical line test, there's no problem with them everywhere. But continuity doesn't mean that we can derive. Okay, and is the derivative, you said 65?
No.
63.
I just had 64.
Just 64.
Yeah.
Okay, you said 2, but
Oh, sorry.
it's okay. Okay, alright, homework.
The last one was 48, right? For 2 dash. Oh, God, I said this backwards.
I don't remember off the top of my head.
Jonah, it was, the last ones were 23 through 26 on 2 dash 3, right?
Yeah, 23 to 26.
Sweet, I did it all.
Okay.
The only ones from this homework packet were just
There's a bunch of 2 dash 2 and then a couple of 2 dash 3.
Yeah. There was only a couple.
How many pages?
Also, you could probably fast forward this part a little bit. Just getting homework.
For your information, 25 through 32 is the second boxes. That's the double prime. I didn't
Okay.
want to take a whole other page to put that there when I had space.
I don't get you guys trying to save paper. I try to see how much paper I can use.
I know you do.
My homework is like 19 pages.
Oh, the homework you scanned to me was a bunch of pages.
Hey, my homework for him for the last week packet was like,
That was a lot of pages, but it was fewer than my goal.
Wait, actually? Dude, I average like 6 pages per homework.
There's like 2 problems on a page
And then turn it
what's your size of font? Like 12?
15.
definitely like 26.
I use title font for everything. I don't even use like the something.
a title font bold.
Okay, guys.
Spaced.
Here we go. We started talking about the antiderivatives on Wednesday.
Hey, be happy.
So just to give you a little bit of vision of where we're going. We're gonna keep exploring. This is kind of a little like side topic that we're doing right now. We're gonna come back to antiderivatives and like modeling motion and those application problems. We're gonna come back to all that later. But I'm just introducing the ideas right now. These exist. We can think about them. You're ready to understand them, but we're not gonna dive all the way into all of the details yet. What we're gonna do next week is we're gonna start, so we have been looking at derivatives of polynomials, which are easy. We're gonna start looking at derivatives of exponential functions and logarithms. We're gonna start looking at derivatives of trig functions, which we've already started a little bit, a little preview of those. And then we're gonna get into what happens if I have polynomials and exponentials and trig functions all in the same function. What do I do then? So we're gonna see all the different scenarios that we can run into. Those will be our next few weeks. No, fine, it's fine. Okay, so the antiderivative, just going backwards. So that's that. Notation is the capital F, and then we saw, okay, we're taking just the antiderivative of this. This is a correct answer, is x to the third. That is a correct solution. And then so is this.
Yep.
Yeah, anyways. And then we're like, oh, but what if we have a constant? We couldn't know. If I had given you x to the third, you could never have guessed that I had a plus 5 at the end.
Yep.
You would have never known. You could have never known that I had this ridiculous fraction at the end. Nor could you have known that I wanted all of this ridiculous trig values if I only gave you x to the third. Okay? And now I've moved everything. Okay. So, this is our theorem. If you didn't finish writing it down, here you go. But if we take an antiderivative and we just pretend c is any constant, then the antiderivative plus a constant is just another solution or another antiderivative of whatever function I gave you. So you could have any sort of kinds of things going on. So actually, are you writing this down, Michael?
Yeah.
Okay. I actually prepared a visual of it, so when you finish copying it down, I'll show you that we can see that visually, graphically, the different solutions to the antiderivative.
Okay.
This is also in your book, so when you read, which you guys read yesterday, that section actually, so you already read it. Yes?
How I fail to see how this is helpful if we can't like derive any sort of constant. Like I don't know how you would even like find this like the antiderivative useful if you can't actually figure out what the original equation is with a constant.
Yeah. You're not going to feel that way
Oh. Is there a way?
after today, and you're also not going to feel that way second semester. So. But that's a great question. I mean, that's a valid concern. How is this useful? That's a good question. How is this useful if I can't actually know the function? Because the function plus 5 is very different from the function minus 3. But remember, what does the derivative tell you? The derivative tells you the rate of change. So the rate of change remains the same in all of these functions.
The slope.
The slope of this function is all the same. It doesn't matter how high you shift it up or low you shift it down. The rate of change will remain the same.
Just the constant just changes the y-intercept.
Bingo. So here you go. Here's our 1/4 x to the 4th that we found the antiderivative of. This is the antiderivative because it was x to the 3rd that we took the antiderivative of. All of these different constants are just shifting it up and down. You can have c be anything that you ever could want it to be. Just have all these random decimals and whole values, but you see how it just is shifting it up and down. There's an infinite number of these that you could create using that c constant. And you could do ridiculous stuff like the trig values, or you could do, you name it, throw pi on the end if you want to. But you can have all of these different kinds of functions, but notice that the rate of change is all the same. Right here, your derivative is 0 because it's flat. Right here, your derivatives are positive because you're increasing. And right here, you're decreasing, so your derivatives are negative. It's the same values at all points on any of the solutions. We can even see it with our other one. This was the other antiderivative that we found. It's all just shifted vertically. You can add any kind of constant you like, and you're just, the rate of change is the same. You're just shifting it up and down. Again, you could add a million, it doesn't matter. Throw pi on the end, tangent of 1, doesn't matter. Like, whatever your C value is, it can be anything. Okay? So, what we've discovered is that antiderivatives have a whole infinite family of solutions. And the family members differ from one another by just the value of a single constant. So, how is this useful? In practice, we're often interested in just one solution function, like not a whole family of them, not just one. So one way to specify a unique solution is to require that the function have a particular output for a particular input. Graphically speaking, you just choose one point. And so this means you would choose one solution, one of these curves here, by specifying a point that it passes through. This extra requirement would tell us the single solution for the antiderivative. So if I said, we'll take the antiderivative of this, and the antiderivative should pass through the point 0, 1, well then you know it's the black line.
Yep.
Okay, the antiderivative should pass through, holy smokes.
0, 0.
Sure, it's this red line. It's hard to see any others. I don't know if this is a point.
-1, blue.
Yeah, that one's easy too. The blue is mine. Yeah. So like you could say it needs to pass through this point. Then you have one solution. You'll never have more than one solution because that's the only one passing through that point. Okay? So that's called, that point that we would give you is called the initial condition or the initial value. So I should have prepped these in advance, but I did not. So here we go. We're going to solve antiderivatives with the initial value. So let's just use me. So example 1.
Log in.
Solve the initial value problem. This is commonly abbreviated to IVP. So this is what we're learning today is IVPs. So if I give you the derivative f prime of x, stop moving, f prime of x equals 6x plus 5. And then I tell you that f of 0 equals 2. Let's find the original function f using this information. Okay, so what's the antiderivative of f prime here? First off, let's talk notation. What should I write for notation for this antiderivative?
So do big capital.
Not a capital.
Are we doing the antiderivative?
Yeah, we are doing the antiderivative.
Isn't it capital F?
Yes, but what is the definition of the notation?
Oh, it's called a
If I have the function f, then the antiderivative is capital F. What do I have here? I've given you f prime. What's the antiderivative of f prime?
Oh.
Little f of x.
So it'd be big F. You could also write it big F prime.
Sure, we could write big F prime. That'd be fine too. Yep. That's true. Good connection. Great. You're extending that. If I had written just f of x like this, big F of x. What I'm actually finding is the double antiderivative, but we don't need to do that.
So it'd be 3x squared would be the 6x.
3x squared.
Because you go 6 minus 1, so x,
Mm-hmm. Good.
plus 5x.
The constants are the easy one, you just have to add the variable. Plus c. That's the antiderivative. Right?
Which could be nothing.
Which could be, yeah,
Zero.
could be 0. Let's find out. So I gave you a little bit more information. I gave you f of 0 is 2. So let's, now that we have f, let's just plug in f of 0.
So 0 plus 0 plus 2 equals 2. So c equals 2.
Right, this one's easy to see. Okay? So this should all equal 2. F of 0 is all this junk, which should equal 2. Well, 0 times all this stuff is 0 plus c equals 2. So then 2 equals 2. Oh, there you go. C is 2. Okay, so I mean that's all the steps of writing that out. But c is 2. We're not really done because we wanted to solve the initial value problem. What we need to do is actually write f of x, the actual function. So yes, you found c, you've done the hard work, but now you just have to write your final answer.
So f of x equals 3x squared plus 5x plus 2.
Yeah. Well, there you go, and then you're done. Not too bad, right?
Not too bad.
Okay, so here we go. Give you the next one. You will see that abbreviation on the AP exam. IVP is something you should know what that stands for, and it stands for initial value problem. And this is the kind of stuff you would go through. Just find the antiderivative, use the 1 point that I have to find out what the value of c is, and then write my function. So take a stab at this. You got it already over there?
Yes, I believe so.
Tricked you. It's not plus 3. Keep going, you're doing the right thing.
F of 0 equals 3? Oh, I see what you did. I see what you did. So, prime.
See, it's not
Wait,
listening.
what? I don't see it.
See, it's not listening.
Unless I wrote my answer when I did it.
It should be, because it should be 4x squared plus 4x. Right? Plus 3.
Yeah, plus 3.
I'm like 93.5% sure.
No, but it's also. Oh, I see what I did. Yes, you're right. It is plus 3. But then, what I copied down was, if I then gave you f of 1,
Oh.
then what do we do? 4, I think.
So then it'd be 4.
So, I'm sorry. So yes, let's end this one. Yep, so it is f of x equals 4x squared plus 4x plus 3. Okay, but now if I gave you this one, this is a little harder. So now what would f of x be for that one? Let me just change the color to make it clear.
Alright. So it'd be
So yes, I did copy my notes wrong.
so 4 plus 4. I have it. Oh, that's 4.
Right? Did I do that man right?
Yep. That's what I have too. 4 plus 4 plus 4 plus 4 minus 4 plus 4.
Good. Great. Okay. So there's that one. Alright, then I'll give you one more. And then I think you guys are gonna be fine on this. Again, we're gonna come back to some more complicated stuff later, but 3. I need to close the door. That's getting loud. Roman's doing good though.
I was
I
wondering
got
if
it.
that was
Be better.
Do you teach music here?
No, I can't teach music.
Do you?
Not currently.
Do you do any choir?
I just subbed for choir like 2 weeks ago.
Oh.
Here.
So, I
But
thought
I've
it was-
never really taught a choir before. I learned more about choir that day than the choir students learned about choir that day. That was my first time leading a choir or something. I could lead band. I was asked to be the band instructor, and I said no. Because I'm doing this, so. This is a lot of work. An AP class from ground zero. Did you get there?
Yeah.
Great. Okay, so there you go. That's IVPs, or initial value problems. So that's where now you shouldn't feel like anymore it's useless, because we can find the specific solution we want if I give you 1 point that it should pass through. That's all you need. One value that it goes through. And you can find the unique solution to that antiderivative.
Depression has been postponed.
Good. Next semester, we're gonna be doing antiderivatives like all day long, and it's gonna be way easier, I promise. It's gonna be fun. That's when we do integrals. So, sneak peek. So this is why I wanted to introduce it now, so you can like mull on it for the next 3 months. Okay, let's do, since we're just kind of finishing up exploring these ideas, let's do a couple more application problems, and then we'll call it a day. And we'll go on to exponential functions next week. Yeah, not too bad.
I actually like. I'm still like understanding everything. No new stuff.
Good, I hope so. I mean, we're on a team here, so I want you guys to succeed.
That is me every day.
Okay, this should be a little similar to what we did on Wednesday.
You can't do
It's true. It's fine. I had A's in both.
This would be a kind of question you might see something similar to on the AP exam, and you would not be allowed to use a calculator. So let's do this without a calculator.
So first we define the derivative function, right?
That would be a great idea.
X. That was easy.
Yep, I gave you a nice one.
So
So, what do we do?
So
Let's think about maximum, minimum. How can we think about it?
let's just envision the graph. It's gonna be
Good idea. Which graph are we looking at?
sorry, I'm looking at the F prime graph right now, mentally. Just looking like this.
Okay.
And because we're trying to find the maximums and minimums. We know they're gonna be when F prime equals 0, right?
Okay. What will be?
So if F prime equals 0, we know it's either a maximum or a minimum.
Good.
And then, so we know one of them is 3.
Right.
And then that's the only one we know.
Because we can plug 0 in here.
Yep.
And then solve. But we don't know for sure yet if that's a max or a min, but it's one of them. Okay. All right. We want to find the exact values of max and min on f of I. So
then we can kind of, then is it you just kind of think about what the graph's gonna look like?
yeah, well, I mean, we can think about that. What does it generally look like?
It's still gonna be, it's gonna be linear.
Which one?
The f of x.
It's not going to be linear.
Oh shoot, yeah, it's gonna be one of these.
It's going to be parabola. Right? Okay, so it's going to be a parabola.
So
We're looking at 0 to 5. Okay.
we know there's a y-intercept at -3. Yep. Wait.
Nope.
No, we don't know where the y-intercept is.
Well, we can, actually, in this case. We're just plugging 0.
Oh, so then it'd be
You
0.
get 0, 0.
Oh wait, that actually is helpful because then we know the 0, 0 is gonna be the
Farthest left point.
and it's gonna be the farthest left point. We also know it's gonna be the bottom. Is it the middle? Or do we not know that for sure? I guess we plug in negative 1/2. Yep. It's gonna be greater than 0. So we do know that's one of the minimums, right? 0, 0. Because you plug in -1. If you plug in any negative number, you're gonna get a number that is above 0 because it's going to be a small positive number plus another positive number, and neither of them can be negative, the negative side. So we know it's a minimum. Oh, but it could go lower on the right side.
could just plug in some points and see what happens.
Yeah. So
Well, we found one special one.
0,
at
0.
3. Let's see what 3 does.
okay.
So f of 0 is 0. Right?
Yeah.
Alright, f of 3.
4.5 minus 9. So negative 4.5. So we already know it's not going to be a.
Might as well try our other endpoint.
25. So 12.5 minus 15. So negative 2. Negative 2. Yeah, negative 2.5.
Okay. So we can give ourselves a little graph. We have 0, 0.
Oh wait.
3, we're gonna have negative 1/2.
Oh, I understand it now.
5, we'll have negative 2.5.
Oh, so we know the maximum minimum because we know 3 is going to be one of them, and we know it's not the minimum, so it has to be the maximum.
What's the maximum?
3.
No.
Sorry, 0.
Yes.
Yeah, and then 3, the derivative of 3 at 3 is going to be 0, so we know that one's a minimum.
Okay. So then now we just need to make sure we summarize what we've written. A min at x equals 3, which is negative 4.5, and a max at x equals 0 of 0. Nice. Okay, I don't know that we really have time for either one of these other ones that I have written down.
We could just zoom.
We just what?
We just zoom.
Oh, just get out of here.
No, I mean speed run math.
Oh, sure. Maybe. I think we could try this one. Alright, I'll try to write fast. I think this is example 5.
Yeah, 5.
Okay, here we go. It's not going to be the nicest handwriting because I'm going fast. Cannonball is shot upward.
Right, here's the first
Yeah, I know she is. From an initial height of 5 meters with initial velocity 90 meters per second. We want to answer A. How high does the cannonball get? And B, when does it hit the ground? Terrible handwriting. Okay. So, cannonball shot upward from initial height, 5 meters with initial velocity 90 meters per second. How high does the cannonball get? When does it hit the ground? What kind of tools should we use?
Well, we know the graph is going to be time meters.
True.
Or
This would also be something you'd see in AP exam. Can't use a calculator. But
we know the at 0 seconds it was 5 meters up, so that could be our y-intercept.
yeah, so we could start to draw a picture of what we're looking at. And obviously then we can just chart its path. The cannonball goes up, and at some point it goes down. Right?
Are you making the y height?
I'm making meters the height, the y, and seconds the x. So we know it's gonna be an inverse it's gonna be is it gonna be a squared root? Since it's a flipped parabola?
You just use a negative to flip it.
Oh, good point. So it's gonna be squared to the negative half.
What kind of functions, formulas should we use to try to solve this?
We probably have to find
What's making the cannonball fall to the ground?
the gravity. Oh.
Didn't we do this with the football guy?
Yeah, similar.
Is it the exact same?
Nope, it's different numbers and different I'm also asking you part B. I've only ever asked you A. You weren't able to answer B yet. Okay, what is the formula? Because I know antiderivatives, I just have to remember one of them. Are we going to use the metric or imperial system?
Imperial. I don't know where my sheet went.
Imperial is American system.
Mer.
What are our units here?
Seconds. Meters. Oh, so we want euro. I just said seconds. Wow.
Okay, so we're going to use the metric system. That's negative 9.8 meters per second. All I have to do is remember this one, because now when I take the antiderivative of that, when I take the antiderivative of this constant, I get the constant with a variable plus some constant. If I take the antiderivative of that, I get that constant's going to take a variable and we're going to add a new plus c. But we'll just rename plus c as h naught.
Okay, so.
Cool? This is why antiderivatives are actually really great.
This is actually kinda
all
sick.
we have to remember is that number.
That's kind of cool.
All I need to remember about gravity is that it's negative 9.8. Because then this is just your plus c. And there's your plus c to the plus c. Okay. So, what else do we know?
So we need our.
Do we know our plus c's? Yep.
Our velocity over time, is that meters to, is that the meters per second? 90?
That's our initial velocity.
Whoa. We're getting closer.
That's our initial velocity. What was our initial height? That's what h naught is.
5.
Yeah, 5 meters. Okay? So we can remake our equations now that we have our plus c's here. I'm so glad that you think this is cool. I think this is cool too. H of t will equal negative 4.8 t squared plus 90 t plus 5.
So height stands for maximum height, correct?
Height is just, that's your like the function that we graphed here.
Height,
This would
like,
be h of t.
seconds, yeah. Okay.
Yep.
So that's our equation.
Yep, so these will be what we can use. So now we actually have everything plugged in. So now what? What are we trying to answer?
How high does the cannonball get? So we want to figure out at what point the f prime of that equals 0.
Mm-hmm. Because that will be the maximum point right here when your derivative is
So we
0.
plug in 0 for that, and it's
For what?
So in the v of t equation,
Right.
so it'd be
We're just actually not going to plug 0 in, but we're going to sub 0 for v of t.
for t, right?
Not for t,
Oh,
but
for
v of t. We want to know when that
Oh,
function is 0.
So then it'd be 90 divided by 9.8 would be the correct. Wait, what the heck am I saying? Wait, hold up. Yeah.
Mm-hmm.
So it'd be 9.183.
Yeah, let's go to 4 decimal places. So at 9.1837 seconds is when that velocity is 0, but that doesn't answer our question. How high does the cannonball get?
So then we plug in that to our equation, our h of t equation. So plus 90. Oh no.
Our phone is over.
Plus 5. 876.53 meters.
No, but I don't know what you did wrong.
4.9 times 9.
4.8. Wait, 4 point. Oh yeah, 4.9
Times that number.
times
9.8183.
times that number squared.
Oh, I didn't square it.
There you go.
I didn't square it. Dang it.
Oh, it's too bad because I had a really fun problem. Even more fun than this one. We'll do it another time.
Plus 90 times 8 plus 1,244. Dude,
No.
are you sure?
Yeah, I'm sure.
4.9 times 9.18.
Negative 4.9.
Oh.
The
God.
details matter,
Dang
Michael.
it.
Is it 418?
That's really close, but you probably only put in 9.8, right?
No,
9.18. You put all 4 decimals. Okay. This is probably because I added more decimals past these ones. Like if you just do answer is easier than typing the decimal.
That's what I'm doing right now. Alright, 427.
There you go.
Yes!
Yep. 418 is close enough. So you did the right thing, but he just used more decimal places than you, so that's why it's different. So that's a good lesson, and don't round until the end of your answer.
When does it hit the ground? So then it's acceleration.
Well, that's an interesting thought. But let's think about it this way.
Oh, right.
When on this graph does it hit the ground?
Oh, when h of t equals 0.
Yes.
You'll have to
Yes.
send some to us.
Oh.
I really want to see it.
I
I saw your
plug in-
profile picture. It's so
I know, she
Zero.
finally sent all of the rest of the.
Your eyes
yeah.
look so good
Oh,
in that
thank
picture.
I know.
So how do we find
So great.
roots of something?
Derivative. No, wait.
That's not great to change. But how do we find where this equals 0?
You algebra?
Yes. What alphabet?
My 5. That's a slow way.
That's very hard.
Folder the parrot in your folder.
Oh yeah, that's for art class.
Oh, we'll play our six.
Yeah.
Inverses.
pretty big.
I did.
I went on a date with Eddie.
What'd you do for yours?
I don't know.
I did a
Can
match.
Yeah, you always did.
You always can. It just gets messy.
What happens if I don't have easy
I
factors?
can't find my
You gotta
my
divide
story.
it. Long division. Oh yeah.
I can't find my story.
Long division.
Oh yeah.
Long division.
No, I was so
Wait,
bad.
I literally said division. Oh well, that's not. Yeah.
Oh, that's the
Quadratic
the
function.
the. I don't know about it. I remember that.
That's a square.
The quadratic formula. I said that.
All right.
It's so obvious, Michael.
Finish
Duh.
that on your own time. Find the root.
Veggie
I'm messing
How-
with
what-
that.
Not really. That's
that
okay.
animal is in the ground.
That was legitimately the coolest thing I've done in 4 years of Two Rivers
Oh, wait.
Classical Academy.
Hey, will you stop that video for
Oh
me?
yes.
Wait.
After I say hi.
Let's see.
Yes.
Michael, did you
Okay.